This talk is from linear algebra to machine learning. Well, I want to talk about basically some NumPy functions and also some basic TensorFlow functions, which are the same as the NumPy functions, and how linear algebra can help us to understand what is happening in some small classification problems. Basically how to connect all of this, NumPy, linear algebra, and machine learning. Oh, sorry. Apart from linear algebra, some other things that we need to learn in order to go deeper in machine learning is calculus, obviously, probability, and statistics. Lastly, as we know, machine learning is some hype topic, so everyone wants to do machine learning. As far as I know, or as far as I want to do it, it's better to go for the hard path. That is, it is better to learn the theoretical concepts in order to understand what is happening in the data science. So for that reason is that the most important positions are taken by mathematicians or physicians. I don't like that because I am a software engineer. So, but still, in my opinion, it is still some path to go from software engineer to data scientist. Maybe it's harder, but it is worth to go and learn these mathematics concepts. So this is a kind of very basic talk. Mainly, I will say some things about linear algebra, as I said. Apart from linear algebra, I want to talk about vectorization. When I start to learn machine learning, I did it in the wrong way. I mean, this is some implementation for matrix distance. And as you can see, there are some for loops, some indexations that are not quite efficient, but well, still this code is working, and I could okay, also some, this is my Euclidean distance implementation. This code was able to do what was supposed to do, but it was taking a lot of time. So I didn't start in this way because I didn't know the vectorization. So let's start talking about vectors. Vectors are simply a collection of numbers. Usually we find in the books with some arrow above or in bold notation. This is not that important, but yeah, it is. Yeah, there are a lot of small things that we should know. For example, how to calculate the length of some vector. It is this formula, and we can do it with NumPy and TensorFlow in this way. As you can see, when TensorFlow was implemented, they just took the same names and the same notation as NumPy, which is good. Another important operation with vectors is the calculation of distance. Here, as you can see, this formula, the Euclidean distance, is the same as the norm. So we can calculate the Euclidean distance using the norm function. Once again, it's almost the same in TensorFlow. Another important operation, maybe the most important one, the dot product. So yeah, once again, it's quite simple. I mean, in NumPy. Yeah, we can do something like this, like just call the np dot, or just, or also we can do exactly this formula. Yeah, we are using vectorization. TensorFlow is almost the same. One very important concept for me, or detail, is that usually the norm, the distance, the length of some vector, they are very similar, and we can do some kind of some good, how can I say, we can derive some formulas. In this case, it's easy to see that the dot product of the same number, it is actually the norm squared. So these two codes will be the same, will give us the same result. It is somewhat important to take this into account or internalize this, because we don't always have the implementation of some functions, some distance functions. Then when we want to do it from scratch, we maybe these concepts, if we have, if we know it, if we have these concepts internalized, we can go deeper. Okay, so as we know, matrix multiplication, we need to yeah, it is only assume. I mean, we go from row, the column of the second matrix, and then we will get another matrix. Yeah, this is easy in NumPy and TensorFlow. Okay, so we'll go for some examples. Yeah, I don't know if you know this stuff that is kind of funny these days. Like some people is saying that the artificial intelligence, winter is coming. Yeah, maybe it's not coming. Yeah, actually, it's not coming. But this idea is very funny because actually we had some winter before. It was chaos because some guy published some paper, and this guy proved that a single perceptron is not able to solve the XOR problem. Yeah, I want to show some small code showing that it's possible to solve this exclusive OR problem using only one error if we change a little bit some concepts. Yeah. And also I want to show some small lines of code implementing linear regression, use multiplying some matrices. Yeah, so let's go for the idea of linear regression. Yeah, the idea is to minimize the distance, to draw some line which is able to minimize the distance between these points and the line. So we want to find, in the case of the two-dimensional data set, the intercept and the slope of this line. So this is the most simple case. Yeah, this is the notation that we usually see. This is the matrix notation. The solution is this one. So we will skip the steps for going from here to here, but you believe me because I am the speaker, because I saw this on internet. So yeah, this is the solution. Oops. So give me some moment. Okay. How many of you are working in machine learning or data science? I mean, how many of you are deeply interested in machine learning, even if you are not working? Okay, yeah. So do you recognize these small data sets? If you see, they are more or less different, but they draw the same line. So they are called the quartet Anscombe. And yeah, the idea is to show or to visualize the concept of correlation. And is very famous data set for this purpose. So yeah, here I have some function to, can you see the code? I can increase the size. So everything is here. Like, this is what we need to do. Just take the data set and apply some operations, some multiplications. Oops. Is here. So yeah, it's not very clear, but if we go from here, we can see the transpose of this data multiplied by the data, which is here, and yeah, the rest, and we get the solution. Here is some kind of preprocessing steps. We are adding some column, adding number ones, which are actually here. There is some multiplication with some bias term. So whatever. So yeah, we just send this data. I mean the y and the x. So the data set and the corresponding labels. Not labels, but the corresponding values. We will get the solution, the W, which is containing the slope and the offset. And then we just plot this. Yeah, I am taking these small data sets as it was supposed to be. They draw the same line, so it's working. Yeah, the point is that having the concept clear, we can just do some matrix multiplications, and this is some basic machine learning. We also can do this with TensorFlow. So we know that the vectors are actually one-dimensional tensors. And then we just apply the concepts, or we apply the TensorFlow idea of coding, and we create some placeholders, and we do the same multiplication. Well, actually, it's very ugly, this code, but it's working. And then, yeah, just run the session with the variables that we define in our placeholders, and it will work. Yeah, we just did some matrix multiplications. Now, what I said before, I want to implement a simple perceptron. Well, not exactly a perceptron, some neuron, and then with this simple neuron, we can solve the sort problem. So the idea is not use the same kind of neuron, but instead of using some monotonic function, we can use some non-monotonic function in the neuron. So yeah, usually the best way to, or the best idea is to use monotonic functions as the sigmoids, but we can use some non-monotonic function. In this case, this is just the data set. We can see that it's some sort data set. So we need at least 2 lines to classify this data. But if we use a non-monotonic function, we can do it with just 1 neuron. Let me check here. So what the function that I did use was a cosine function. If you see, in this first visualization, it is almost classified. So you can see that it is, I don't know if you can see the gradient as going up and then going down, and then again going up and down. So it's imagine some cosine function in 3 dimensions, and then we can do the classification in this way. So actually, it was possible to avoid the winter, the artificial intelligence winter, like 50 years ago. Well, it was not possible, but we had some enough mathematical concepts. So it's very interesting historical stuff. Yeah. So yeah, these 2 basic examples is those that I wanted to show. And basically what we are doing is just doing matrix multiplications, and we are not using for loops. So it is, again, good idea. I mean, again, as a conclusion, it is good idea to go deeper and deeper in the mathematical concepts, and this will give us some kind of different mentality to solve data science problems. So what else we can do with linear algebra. The most important algorithm these days is the gradient descent, and is basically the implementation a lot of matrix multiplications. Also, another linear algebra concept, the important linear algebra concept in data science is the eigenvectors and eigenvalues. Is the base of dimensionality reduction. Yeah, also because sometimes we are using very, very small numbers or very huge number, we should be aware of numerical instabilities. Yeah, some material that, in my opinion, are worth to check is this specialization by Coursera, and also that they have 3 courses. Is a good one. Do you know this guy, Siraj Raval? Well, he's very famous. He explains the mathematical concepts as a comedian. Sometimes he's leaving some gaps, but actually he's a very good one explaining. The deep learning book has some chapter where they list which concepts we should learn for mathematical concepts. Even when it's not a good material to study, we can check at least which concepts are important. Yeah, that's all. Do you have questions or comments?
In the beginning of the talk, you compared 2 solutions for the matrix. Can you describe why one is faster than the other? So this is just because the library seems like the C and the loop is Python.
Oh, okay. In this case, actually, yeah. He's asking for why this is slow or why the other operations are faster. The idea of this implementation is that even when we have for loops in R, this is implemented in R or Python, it is not good idea to use it because they are not running on compiling time. Yeah, they are not compiled, so the implementation will be slow. So it's preferable to use the vectorized functions that in the case of R are already implemented in the core language. And in the case of Python, we should use NumPy and SciPy to use you just call these functions. For example, here it is the same logic, like just multiply the elements of 2 vectors and then get the sum of these ones. It is the correct way to do it in Python. If we are using C or C++, it doesn't matter. We can use for loops because the management memory is the best one. But in the case of Python and R or MATLAB, it's not a good idea. Yeah, it is a common error for some people. I mean, it was my case. I don't know if it was your case someday. Yeah, some more questions or comments?
Could you share your Jupyter notebooks and where?
Ah, yeah, that's right. I will share it in my GitHub account. So this is the URL. So actually, the material is already there, but it's not updated. So I will push some update in this repository. So, any other question or comment?
Can you explain the export problem? What that was about?
Yeah, okay. Well, the other guy was asking about the repository. Now, I want to explain better the sort problem. So the idea in the sort problem is that we don't have a single line to separate this kind of data. If we draw some line over here, the separation will be not correct. So what we need to have is two layers in order to draw another line. The first perceptron was one single layer, so it was working, solving some problems, but then it was this guy Minsky just published some paper and he showed that it was not good idea to use the perceptron. So, but this was solved later, but then we lost around 10 years of research on neural networks. Yeah, well, it's a funny history. Yeah. Some other question? So we'll, thank you.